Okay, good morning, everyone. Today, actually, we'll have 3 weeks instead of 2 weeks to talk about graph theory. So that's very good. I'm not quite sure about the first week of December, but it turned out on this term, the first week can still teach. So it's good news for me. I think I can talk more on about graph theory, because which is really very important and very useful in practice. Okay. So starting from today, we'll talk about graph theory. All right, so let's start with two questions actually. One is here I have 2 graphs. So I haven't really formally introduced what a graph is. All right, but I think you can see from picture, I have 2 pictures about 2 structures. The question is, do these 2 graphs have same structure? So technically or mathematically, the question is, are they isomorphic, which we will discuss later. All right. Another problem is really an application problem called social distancing. So actually, this is a problem we are facing nowadays because of COVID-19. How can we keep distance in order to prevent the spread of the virus? All right. So what we need is, suppose each point represents a person or table or whatever. So that there are distance requirements. So for any 2 persons, the distance should be at least d. All right. Now here it's easy to see that for some pairs, their distance is too small. So what we can do is remove one of the points. By removing it, we can mean maybe one person should wear mask. So if these are close, at least one person should wear mask, for example. Or really physically remove that person. So that person should not be maybe in that restaurant. So it will be not allowed because of the distancing. Or move this person to somewhere other place. All right. But the point is, we have set a point here. We want to remove minimum number of points. Of course, the easiest way you remove everyone will be mask. That's very easy. But of course, then economically, it's not very good, not efficient. It's a lot of waste. Everywhere mask. So 7 million people in Hong Kong. So we will need 7 million masks. That's a lot, right? So what we want to is remove minimum number of points so that after we have removed these points, then the pairwise distance is at least d. So how can we do it? All right. So for this problem here, we want to remove minimum number of points so that for the remaining points, minimum distance will be at least d. So there's a specified distance, maybe 2 meters, maybe 10 meters, depends on application. All right. So how can we do it? So actually, it can be modeled as a graph problem. So what happens is we can construct a structure called a graph. Okay. So we'll formally introduce the notion of graph in a minute. All right. So what we do is use a line to connect 2 points if their distance is less than or equal to d. So for example, there will be a line between these 2 if their distance is smaller. All right. So in our application, what means if there are a line between 2 points, we have to remove at least 1 point. Otherwise, these 2 points will be too close. All right. So we can construct graph. So for example, these are too close. So perhaps there's a situation. This one. I guess something looks like this. Maybe like this. I'm not 100% sure about this one. Okay, so this one maybe here. Maybe this look like this. Okay. So eventually we obtain a structure. The red one plus these blue ones. And what we want to do is find actually is the classical vertex cover problem eventually become vertex cover problem. A classical vertex problem. We want to find the minimum number of points, these points, to cover all edges. So the problem is really to find so technically instead of points in graph theory we call them vertices. And the minimum number of vertices to cover all edges. each line is called an edge. All right. So by color, what we mean is if I choose this vertex, so that will cover these edges. All edges that's connected or has relation with this vertex. Technically, it's called incident edges. Incidence edges. So this vertex, it will cover all edges. So for this application, what does that mean? If this guy wear mask, so these people do not need to wear masks with respect to this one. Of course, these two are too close. One of them need to wear mask. But with respect to this one, once this person wear mask, then none of them need to wear mask. Then of course, the two relate when we study relation among these, then for these two, one of them needs to wear mask. Maybe then we use this one to cover it. So that will cover this edge, and cover this edge, and so on. So for this one, perhaps I don't know the solution, whether it's minimal or not, I don't know because it's a very difficult problem in general. All right. So for this one, if this one is not, maybe it does not look to be very efficient. So I think this one, I guess it's optimal. Okay. So needs these 6 people. Either remove them or ask these 6 people to wear masks. Then the whole group will be protected. All right. So that's one example of application of graph theory to solve practical problems. It has a lot of applications. Actually, it's really universal. Graph theory is really universal. In connection with computer science, actually all computational problems can be modeled as a graph problem. Okay. So we can really regard this one as a universal tool for computation, a universal model for computation. The graph can be regarded as a universal model for computation. The reason is whatever we do, we do in computer, of course, computer program. What we do is as time goes by, we change the content of some cells or registers or memory cells in the computer. We change their status. All right. So the number of cells, computer cells, memory cells, or register is finite. So whatever it is, the current status of a computer can be modeled. It can be long, so it's a vector. Current status. It can already be modeled by a vector, so maybe x1, x2. So nowadays, this n can be huge. Can be huge, maybe 10 to 10s or whatever. It's huge, but regardless, the status of computer can be always described by a vector. It's uniquely specified the current status of a computer. So it's called a configuration. All right. So what we can do is to use a point to represent the computation. As time goes by, what happens is status change. So change from this status to another one, maybe to another one, this one to this one, or this one maybe go to here and here and here and here, whatever. Just status change as time goes by. So eventually, computation asks us whether it's possible, maybe goes from initial configuration to our required configuration. Maybe this one, required configuration. So whether it's how we can get from initial configuration to the required configuration. So maybe use minimum amount of time. So perhaps using minimum amount of time. So what happens in this structure? We're looking for a path. So we follow these arrows to move along. So we're looking for a path from initial point to the required point. So that the length of the path indicates that actually any computation can be modeled as a path problem. It's a path finding problem. We start from initial condition to a required condition, from initial configuration to required configuration using minimum amount of time. So that translates to shortest paths. That's really a shortest path problem in a graph. The problem is this graph is huge. It's a huge graph. Okay. So the problem is the searching space is huge. So we need to find effective ways. We cannot really work on this graph. So we have to find clever ways to find such a path instead of search this graph. It's usually there is implicit graph behind our problem. And then not usually, always there are underlying graph. Let me give you a concrete example. Okay, let me give you a concrete example. That's a Rubik's Cube. All right, I don't know whether you played with it or not. Okay, Rubik's Cube. A Rubik's Cube have 12 different movements. So 6 are face, so this front maybe. So then it's called right, left, top, bottom, and the back. So each face I can turn clockwise at 90 degrees or anti-clockwise clockwise at 90 degrees. All right. So each movement will transform the tube for different configuration. So what happens? The problem is I have initial configuration. So this one, for example, this one, this is not fully restored. It's almost restored, not fully. So this side, you look at this part is not. Okay. All right. So what we want to do is we want to restore the Rubik's Cube. So then for initial configuration, we have 12 different movements to a different configuration. So each edge we can label it, for example, clockwise 90 degrees, anti-clockwise 90 degrees, and so on. So maybe this bottom part, the bottom anti-clockwise, here bottom. All right. So there are 12 different movements. Each will transform the Rubik's Cube for a different one. So if I turn 90 degrees, give us different configuration. So if I turn this way, let me see which one is it. If this front, so top 90 degrees, so give me a different configuration. If this way, different configuration. All right. So eventually, the problem needs to solve. We want to fully restore it. So this is the required configuration. I can have a huge graph. It's very huge. All right. So to restore it, the problem is really to find a path from this one to this required configuration. Of course, if we want to restore the cube as fast as possible, we want this path to be as short as possible. It has been proven by computer. For any initial configuration, 20 moves will be sufficient. And that's the best possible. There are configurations that need 20 movements, 20 moves. For human, at least 50 or 60 movements. For all ordinary person maybe over 100, 200 moves in order to restore it. And for real experts, they only need 20, 50 or 60 moves because they memorize a lot of things. And the world champion only require 5 seconds or something, below 5 seconds, 4 point something to restore to the Lucas cube. All right. So that's a concrete example how we can use graph to model the problem of a puzzle. This is one of the very famous puzzles. All right. Okay. Now we are getting to the mathematical part of graph theory. We'll introduce some terminologies and define the subject and so on. So let me start with some basic definitions. All right. And the motivation, of course, one biggest motivation is application. There are huge number of applications for graph and for graph of graph theory, because graph theory will be very useful in order to develop algorithms to solve graph problems. All right. So our object is called a graph. Where does it come from? Actually, one is in connection to this course is come from a graphic representation of binary relations. All right. So last week when we discussed binary relations, one way to represent a binary relation is to use a graphic representation. For example, let's see this example. All right. So we consider relations that where the x divides y. We consider this relation x divides y. All right. So we can draw the relation use a graph. It's a graphic representation. All right. So we represent each point, each element by small circles, 1, 2, 3, 4, 6. Then whenever x divides y, we draw an arrow from x to y. So here, 1 divides 2, so we have this arrow. 1 divides 3, we have this arrow. 1 divides 4, 1 divides 6. 1 divides itself, so we have root. All right. So for 2, we have divides itself. It divides 4 and 6. 3 divides 6. And 6 divides itself. 3 divides itself. 4 divides itself. So we get this object. So there's a graphic representation of this relation on this set. All right. So this graphic representation actually gives a so-called directed graph. Because each arrow it has a direction, so it's called a directed graph. And in short, it's called a diagram. So I comes from directed graph. So in short, we call it directed diagram. So every binary relation gives us a diagram. All right. Because this structure actually so useful, but gradually people actually forget it, just ignore its original background. So it's come from binary relation. It's used to represent binary relation. rather than define such a structure directly. So instead of saying it's just a binary relation, we'll define a digraph as a pair. So our definition will be all right. So our digraph, a structure, mathematical structure contains two parts, B and S. Where B called the vertices. So this B called the vertices. This is because this is a plural form. The singular form is called the vertex. Each element is a vertex. So each element is called a vertex. The set of vertices, that is plural form. So B is called vertices. All right, then we have edge E. E is called, these are edges. All right. Now, vertices corresponding to a set S. And edges corresponding to an arrow here. These are edges in the graphic representation. So it contains two parts. One is vertices, one is edges. In literature, you will see that vertices are often called, not often, in older times, they're called nodes. Also called nodes. But now the most theoreticians usually refer as vertices. We're not called them nodes because it sounds more professional. If you talk say nodes, sounds like amateur. I'm just joking. Okay, most people use vertices instead of nodes. Sometimes we use nodes. If we have two different graphs, we may use nodes for one graph, vertices for another. And edges in older times is also called lines. For selected graph, okay, also called arcs. So these are terms, arcs. Instead of edges, one may say arc for each edge. All right. So this structure contains two parts. One is vertex set, one is edge set. Now, B is just a set of elements. It's called a vertex set. And E is okay. So that's a formal definition of a diagram. The diagram contains two parts. One is vertex set, one is edge set, which is a set of ordered pair vertices. So actually, it's binary relation. But instead of saying a binary relation, people use this definition for diagram. So it has two parts: vertex set of edge set. So actually, it's a binary relation on the vertex set. So a diagram is really a binary relation on vertex set. Okay. So it has two structures. One is vertex set. So that's ground set X. E is corresponding to how we define this relation. So each element in the relation will be denoted by an edge. And the first one is a graphic representation of a diagram. So mathematically, it's not the picture. A diagram is not this kind of picture. This again is a graphic representation. Mathematical structure is a pairs, set of vertices and the set of pairs. This partition is going to be of itself. All right. So of course, in practice, very often we use this graphic representation. That's for computer. We cannot use it. Computer cannot recognize it. All right. If you have the drawing, it's difficult to recognize the underlying structure without making errors. So we need a different representation. I will mention that in a minute. Okay, let's see. So let me give you an example instead of this one. Okay. Okay, so formally, this one is a graph. Formally, this one is a graph. So this one contains, so in this case, it's called a diagram. So this one is a diagram. All right. So there's a formal definition of a diagram G. Of course, G is from graph. G from this G from here. G. Very often we use G or H to denote a graph. So that's a convention. We use G or H. If we exhaust the G, we use H. So we can use G. If different graph, we can say G1, G2, or G prime, or G star, and so on to denote a graph. All right. So notation wise, we use it in this way. So formally, this one defines a diagram. So this will give us a diagram. Of course, you will say it's hard to see what it is, right? From we only see pair, this appear, this appear. It's difficult to see it. So the best way is to draw a graph, draw a picture to represent this one. So this one will give us just the following graph. So typically we use a small circle, either empty circle or filled circle, but not matter to represent a vertex. And sometimes we even label it, say A in this way or A in this way, depends. All right. So here we can use, say, 4 circles. Let's see, which way? Let me follow the notes, maybe. A. All right, so we have 4 different vertices, A, B, C, D. So then each edge, A, B, we just draw an arrow from A to B. So this first edge, A, B, of course, that's quite straightforward. BC and the CA and BB. Anyway, this one is called the loop. This one is called the loop. Very often we don't care too much about the loop, so we may just ignore it. Very often. Okay. Then BD and a DB. So that gives us, actually this one represents this diagram. Technically or formally mathematically, this one is the graph. This one is a graphic representation of this graph. But of course, we will say this one is a graph. What it really means is a graphic representation. So in practice, very often we say this one is a graph. It's understood. This one is a graphic representation of this underlying mathematical structure. This one just represents this mathematical structure. All right. Now I have to introduce some terms. So we have this most important fundamental definition of diagrams. Then we have some term in connection with the vertices and the edges and their connection. Suppose we have an edge from U to B. So formally speaking, strictly speaking, E is an ordered pair UV. But often, conventionally, we just use shorthand. We use UV in short to denote an edge. So instead of writing this way, we will just use UV. Right? So UV denotes an edge. So then in connection between this edge and these two vertices, we say U is tail of B, and B is head of E. So because of this arrow, but this head, this tail. All right. Now, if we look at a single edge, we have this situation. Now, if we look at single vertex B, so use B or yeah, B, okay. Then there are arrows going into B, and there are arrows going out from B. So these vertices are called in neighbors of B. These vertices are called in neighbors of B. Notationally, we use N superscript minus. So these are in neighbors. All right. And by symmetry, so these called out neighbors. Each element is called in neighbor. Each element here, each vertex called out neighbor. So this step, sometimes you call the out neighborhood. And similarly, this one can be called out neighborhood, or in neighborhood. That's out neighborhood. All right, some people call it in this way. Each element, each vertex is called in neighbor. Each element here is called out neighbor. And another important notion is degree of a vertex. Degree of a vertex. Just measures how many edges are connected with this vertex. So degree of B measures how many edges has connection with B. All right. So because the law of these edges may be different, one is going into B, one is going out from B. So we think we put them into two different catalogs. One is in, one is out. So therefore, we have in degree and out degree. There are two different kinds of degree. All right. So notationally, we use same as minus plus here. So in degree, we have a minus instead of a superscript. Outer degree has a plus in the superscript. And typically, very often we also use shorthands. We can use the D minus B, D plus B here. Notation. So this one is shorthand for this one. This one shorthand for this one. All right. So meaning is in degree number of edges going into V. So here degree will be in degree will be 3. There are 3 edges goes in. Here number of edges coming out. So here will be 4. All right. So for diagram, if we don't have parallel edges, our definition does not allow parallel edges because there's a set, not multi-set. Sometimes we allow multiple edges. Sometimes when we talk about the digraph or graph, we allow multiple edges. Then we get multi-graph. All right. So in our case, it's not a multi-graph, so the degree equals exactly the size of its outer neighbor and the size of its in neighbor. So really comes number of vertices here, number of vertices here. So because we do not allow this situation, if we allow this situation, then these are not equal. So there are some very basic terms for digraphs. And one more. And conventionally, we use n to denote the number of vertices, m denotes the number of edges. And n is called order of V of the graph. And m is called the size of G. So strictly speaking, when we say size of a graph, we refer to number of edges. If we want to refer to number of vertices, we say order of G. But in literal, it's quite possible that people use size to refer to a number of vertices. And usually it should be quite clear from context. So don't need to worry too much. One problem with graph theory is the terminology. Different people use different terminology, and but most often you can easily tell what it means. So in the literature, you will see when people talk about graphs, there was short paragraph given some basic definition about graph. Even when we talk about graph, we have to say what we mean by graph. Does it mean a directed graph or undirected graph? Does it mean graph has multiple edges or without multiple edges, with loops or no loops? So usually people will make a statement to say every graph in this paper refers to simple connected graph, things like this. Okay, so there are problems with graph theory terminology. It's very not uniform across the board. Different people use different terminology, but it's just close enough. Usually will not cause confusion. Okay, so here are some very basic terminology about the graph. And then I will discuss the graph. When we don't care about direction arrows, then we get graphs. And actually, in this course, we'll focus on graphs. I will not talk too much about digraphs. Actually, the theory on digraph is more difficult than theory of graphs. So basically, we'll focus on graphs instead of digraphs. We will touch something, but just some very basic things about the digraphs. Okay, even for graphs, we only have time to get some basic things. All right, so let me check time. Don't forget. Let's see. Okay. All right. Right. So I graph really come from binary relation, general binary relation. But as we have mentioned last week, binary relation has different properties. One important property is symmetric. Very often relation we discuss as actually a symmetric relation. We have this situation. If the arrow goes from A to B, we also have arrow goes from B to A. So that's a symmetrical relation. For every pair, we have this property. If A is related to B, then B is also related to A. Then what we get is symmetrical relation. Now, of course, in its practical representation, it's kind of redundant if we have this one. Why do we bother to draw so many times arrow from both directions? So it's maybe this B, this B. Okay. It's a real waste of time. We draw direction both ways. It's much easier just use a line to connect these two. It's very natural. Instead of draw it this way, we can draw it in this way. So symmetric relation gives us a graph where we don't care about direction of edges. So this is called an undirected graph. We don't care about direction of edges. In short, it's called a graph. Okay, again, I mentioned when we say graph, sometimes it may mean graph contain both graph and undirected graph. Graph may mean directed graph plus undirected graph. But very often when we say a graph, it actually just means undirected graph. So when there is no confusion, we'll just use graph. If I really have to want to suggest graph cannot contain diagram, graph really means undirected graph, I would say it's explicitly that graph means undirected graph. Otherwise, graph always means undirected graph. In this case, graph sometimes we it also means the graph is possible when we have general discussion, but usually it's mean undirected graph. Okay? So that's the one problem with graph here. Really, it's not uniform in terms of definition. So now from here we get this one, graph without selection on edges. Of course, the binary relation may have loops. This we don't care too much. So in graph representation, we really don't care about these loops. We just ignore them. So we get this representation. Because this was sometimes maybe technically important. For example, when we say talk about transitivity, we include we say the transitive relation, the relation has to be reflexive. So that's for technical reason mainly. Right? The essential part of relation actually is asymmetric and transitive. So this one is not, in a sense, it's not really essential, but just a technical issue. So in a graph, usually we don't care about these rules. In most of our application, we really don't need these rules. So we just ignore them. So for a graph, we don't have rules. Of course, sometimes we can have loops and multiple edges, and we get so-called pseudo graph or multi-graph. But we will not, basically, we will not touch them. Okay, the basic thing is this type of graph. It's called a graph. Okay. So now we formally define the graph. Instead of coming from symmetric relation, it's corresponding to symmetric relation. But formally, we'll define the graph again as ordered a pair of objects. right, now simple thing, relation on S, forget S, relation on the set, ground set. Now edge set is a collection of pairs. The important thing is these pairs are not ordered, unordered. The second set is synced elements. All right. Okay. I think I will stop here and have a break. And when we come back, I will give you still a lot of terminologies. So that's very important. Sets the ground for our discussion. So we have quite a few terminologies similar to what we have discussed on iGraphs. All right. Okay, so let's have a break.